Multimodal AI systems are constantly told to trust the right signal at the right time. When you combine speech, video, text, and physiological data, sensors fail, environments get noisy, and evidence quality varies wildly across examples. The standard fix is quality-aware fusion. Estimate how reliable each modality is, then weight the final prediction accordingly. But here's the uncomfortable question that rarely gets answered. Do those quality scores actually change the model's decision? Or are they just riding along with dataset correlations, missingness patterns, or architectural flexibility? In this breakdown, we're examining a new diagnostic that answers that question with surgical precision. The core idea is deceptively simple, but the implications for how we validate multimodal systems are substantial. We'll walk through the methodology, the experimental setup, the results, and why this leakage-safe intervention should become standard practice for anyone publishing quality-aware fusion architectures. Let's start with a critical distinction that gets glossed over in most multimodal papers: availability versus quality. Availability is a binary mask, telling you whether a modality is even present. Quality estimates the reliability of that observed evidence. An outage means the sensor dropped out entirely. A degradation means the signal is there, but it's corrupted or noisy. Standard evaluations often conflate these two. A quality-aware model might appear to work well simply because it learned to route around missing modalities, not because it actually used the quality signal to weigh evidence. To isolate decision-level reliance, we need to separate modality evidence, availability masks, and quality signals completely. That's where the diagnostic comes in. After training a multimodal model, you freeze the unimodal experts and the fusion router. You keep the sensory evidence and availability masks exactly as they are. Then you shuffle the quality scores across the held-out test set. This creates what the authors call broken queue. You compare it against clean queue, where the quality values remain aligned with their original instances. The marginal distribution of quality scores is preserved, but the instance-wise link between a quality estimate and its corresponding evidence is broken. If the frozen fusion rule was actually using quality to weight experts, shuffling it should measurably degrade performance. If performance stays flat, the quality signal was never driving decisions. This is leakage-safe because the intervention only touches inference-time quality alignment. No gradients flow back through the shuffle. No training data is contaminated. The diagnostic purely tests whether the learned fusion weights depend on the alignment between quality estimates and specific test instances. To measure this dependence, we compute a permutation gap. You take the balanced accuracy under clean queue and subtract the expected balanced accuracy across multiple shuffled quality permutations. Under the null hypothesis that predictions are invariant to quality shuffling, those two scores are exchangeable. We calculate a one-sided permutation p-value using the Phipson and Smythe unbiased estimator, which properly handles permutation testing without collapsing to zero. A positive gap with a low p-value means the model genuinely relied on quality alignment. A near-zero gap means it didn't. But a near-zero gap is only meaningful if there was room for quality to matter in the first place. So the authors report two structural diagnostics alongside the permutation gap. First, oracle headroom, the performance difference between the clean queue model and an oracle that always picks the unimodal expert with the highest true-class confidence. Second, competitiveness, the margin between the top and second-best experts' confidence on each instance. Together, these tell us whether better per example routing is theoretically possible. The permutation gap then tests whether the frozen fusion rule actually exploits that possibility using the native quality signal. The diagnostic was evaluated on two complementary datasets. Stressed is the primary setting. It's a stress recognition task with synchronized facial video, speech, and physiological signals. Crucially, it has highly asymmetric modality availability. Audio only appears in specific interactive tasks, and physiological or video recordings drop out due to acquisition failures. This makes it a realistic testbed for outage-aware routing. CMU-MOSEI serves as a boundary case. It's a sentiment analysis dataset with language, acoustic, and visual features that are nearly fully observed. It lets us test whether the clean queue versus broken queue pattern persists when missingness is largely absent, isolating pure quality alignment effects. For the fusion architectures, the authors stick to decision-level fusion, so the diagnostic tests routing among fixed unimodal experts, rather than representation learning changes. Unimodal experts are trained separately on each modality and frozen. For Stressed, they use WAFDVEC2 for audio, a pre-trained AffectNet encoder for facial video, and Moment 1 for physiological time series. For CMU-MOSEI, they use the official language, COVAREP acoustic, and facet visual features. Two fusion families are tested. The first is decision-level late fusion, comparing uniform averaging against quality-weighted softmax routing. The second is a conditioning-aware mixture of experts, where a linear softmax router maps availability and quality features directly to expert weights. In both cases, the router is trained on aligned training data, frozen, and then subjected to the clean queue versus broken queue intervention on fully observed test instances. The results are stark and highly informative. On Stressed, native quality estimates produce near-zero permutation gaps across all fusion families. Logistic regression, histogram-based gradient boosting, and the mixture of experts all show gaps statistically indistinguishable from zero. The same pattern holds for CMU-MOSEI. Yet the oracle headroom is substantial. hovering around 0.2 to 0.36 across folds. Competitiveness between experts is also high, with median margins around 0.2. Routing could absolutely improve performance, but the native quality signals aren't driving decisions. Why? Because the correlation between native quality estimates and actual unimodal correctness is essentially zero. The quality scores are summarizing generic signal properties, not identifying which expert is reliable for the current instance. To verify that the diagnostic isn't just blind to quality effects, the authors run positive controls. They artificially construct quality signals that are perfectly aligned with either corruption levels or unimodal correctness. When quality tracks corruption, the permutation gap jumps to positive 0.071. When quality aligns with correctness, it jumps to positive 0.346. The frozen fusion rules change decisions dramatically. This proves the architecture and the diagnostic pipeline are fully capable of detecting quality dependence. The bottleneck isn't fusion capacity. It's that the native quality estimates simply don't predict which expert is correct for a given example. This separation of concerns is where the real value lies. The diagnostic cleanly untangles three questions that are usually conflated in multimodal literature. First, is better per instance routing possible? Yes. Second, can the fusion architecture use a routing signal? Yes. Third, does the native quality signal actually supply that routing information? Largely no. Quality awareness in architecture does not imply quality dependence in decisions. Reliability estimates must predict which expert is correct for the current instance, not just summarize generic signal cleanliness. There are important structural boundaries to keep in mind. Stressed's asymmetric missingness makes availability-aware routing meaningful, but the diagnostic explicitly restricts evaluation to fully observed instances to isolate quality effects from outage effects. CMUMOSCI is nearly fully observed, so it functions as a quality alignment boundary case rather than a realistic dropout benchmark. Extending this diagnostic to early or mid-fusion attention models would require an intervenable reliability signal or a representation-level intervention, which remains an open direction. The structural diagnostics also require ground truth labels, so they're evaluation tools, not deployment mechanisms. But as a validation framework, this is exactly what the multimodal community needs. Too many papers report that quality-aware architectures perform well, without demonstrating that the quality signal actually influences the decision boundary. Dataset correlations, missingness biases, and architectural flexibility can all produce the same performance gains. The clean queue versus broken queue permutation test forces authors to prove that their quality estimates are decision relevant. If you're designing multimodal systems that claim to route based on reliability, you should be running this alignment-breaking diagnostic before you claim your quality signal is doing any actual work. Quality-aware multimodal fusion only matters when reliability estimates identify which input stream to trust for the current example. The diagnostic shows that native quality signals often don't. But when they do, frozen fusion rules respond immediately. The architecture was ready to listen. The signal just wasn't speaking the right language. As multimodal systems move from controlled benchmarks to real-world deployment, separating quality from availability and architecture from decision dependence will separate robust systems from fragile ones. If you're building or evaluating multimodal fusion, make alignment-breaking tests standard. The gap between what your architecture can do and what it actually does is where real progress happens.